We are in our last module of Unit 2, and in a way, one of our early, really important modules. Um, we've talked, we have the big three about describing data: shape, center, and spread. Shape we covered pretty early. Center, we had our main two, mean and median. Something I forgot to mention before, you've probably heard of the mode also. The mode sucks. The mode is terrible. We definitely don't use the mode. We replace it with the idea of just describing where the peak of a data is, of a data set, of a distribution. Any specific calculations of modes can be difficult to work with. So I will never say mode again in the class except for to say it's not very good. So moving on to our last module here, module 7 of Unit 2. This is one to mark as being a little higher priority than some of the rest of the stuff. We use it all the time, the concept that we're going to talk about, but we especially use it in the most important topics of the class later on. So just keep that in mind, mark this as high priority. There's a bit of a warm-up question here. So we just want to remind ourselves of the point of studying the idea of variability to save some time, which I'm trying to get better at. We're not going to cover this whole question, and I'm going to skip to the point. So there are two cities here with, it's a bit of a complicated thing that's been calculated. So over the last 10 years, you record the average high temperature for a month. So every day in January, for example, you record the high temperature, then you write that number down. Then over 10 years, you average all of those. So there was 10 Januaries. And so one of these dots represents maybe it's not January, but the 10 Januaries of each day average, the high of each day. Okay, so apparently one of these cities is New York City, and one of them is San Francisco. And so which city makes more sense as which? So if you're familiar with the weather, the average high temperature in degrees Fahrenheit of the cities, you will probably recognize that city A is San Francisco. The weather in San Francisco is always, for LA people, you'd probably say, Southern California general area people, you'd probably describe it as a bit chilly. And, you might be joining us from somewhere else also. Compare that to New York, so always in that like 60s and 70s. Every now and then it goes a little higher, a little colder, but there's also not a lot of variation over the course of the year. There's not as much of the seasons there. Compare that to city B, so you can see one of the months has an average high temperature of only a little above 35 degrees, and one of the months has an average high temperature of almost 85. And so that would be New York. New York is one of those areas that has all the seasons. It's cold in the winter. It's whatever, medium temperatures in fall and spring, and gets a little warm in summer. Okay, so, but it turns out each of these cities has a very similar median. So if you just said, what's the typical temperature, and you chose to respond with a median, you'd actually get similar answers. So one of them is 60, and one of them is 63.5. And you could go and check and see what the difference is, but essentially one of those is one of those the other. I'll skip that. And so we learned about the 5-number summary before. And so here we have the 5-number summary. You can see the minimum is 57 to 70 with the quartiles there. City A was San Francisco. City B was New York. And so you can see the difference. We calculated that concept called IQR, how far away these are. 61 to 67.5 is only about 6.5. 45 to 75.5 is 30. Right, so one of them has an IQR of 6 and 30. An IQR is meant to describe the spread of the middle part of the data, which is normally the most important part of the data. Okay, so that was also a bit of a warm-up question. So we're going to move on. This topic we develop quite slowly because it is, it's not super intuitive and it's super important. I'm kind of balancing those two ideas. Okay, so here are exam scores for 11 students. The mean is 70. One thing that I think comes up in the Canvas notes, which maybe we didn't have an exercise for directly here in these workbook notes, is the idea of how to visually understand the mean. And so it's quite quick. You have probably already read about it, but it's also why the mean is represented as a, so the mean here visually is this blue 70, and it's specifically that triangle there. And so the triangle is trying to make you think of like a teeter-totter. And so the mean is considered the balancing point. If these were physical objects, so each of those dots were the same size object, a little Lego or something like that, and you put them on the data where they represented it, the mean would be the balance point. And so the mean is wherever it balances. And you can just estimate this visually from now on. From a histogram, you don't have each individual data point, but you can still roughly estimate it. Okay, so which score varies the most from the mean? So we want to look at all these values here and decide which one varies the most. Normally I get two sets of answers here. I get 60, 80, or 70, and those are in two different categories. So 60 and 80, how far away are these from the mean? Either one, whichever one you might have chose to answer, are 10 away from the mean. And sometimes we don't realize in the beginning that we could actually choose 70. 70 is the mean, but there are 3 values of 70 in the data set, and so those have a distance to the mean of 0. And so which score varies the... Oh, sorry, I did the next question. Which scores vary the least from the mean is what I was just answering there. So what answer varies the least? 70. What is the distance? 0. There is only one good answer there, and I usually always get that same answer. The score that varies the most is either going to be the min or the max, and so that's either going to be the 100 or the 30. How far away from 70, so which one is further? And so that's going to be 30 is 40 away. The score is 30, it's a distance of 40. Okay, so this concept that we are calculating, this distance from the mean, relates to the idea of standard deviation. This is a 3-star important topic. They don't actually call things stars, just however many stars you imagine being the most, this is one of those most important topics, especially early on here in the class. So if you have the printed set of notes, mark it. If you have some way to bookmark it in the PDF version, you can bookmark this this page and this definition here. Flashcard the definition. So statisticians invented standard deviation to measure variability about the mean. It's a bit of a professional sentence. So one thing, this is invented. So stats is some stats is natural, but a lot of stats is very invented. So it's a little messy, has a lot of pros and cons every time we do something. For example, trigonometry and geometry don't feel invented, they feel a little more discovered. Right, so as a comparison. Right, so what is the standard deviation? The standard deviation is roughly the average distance that the data points vary from the mean. So the standard deviation is the average distance from the mean, roughly. And so we are going to start with an intuitive definition, and then we're going to give you formulas and specifics later. Right, so how do you estimate or calculate standard deviation? And this is going to be an estimate. It's going to turn out to be a little different later. And no matter what, formulas will be done on software, so this is still going to be a good idea. Okay, so here's the data set here, just kind of written out in the little table form. So on the top row is each of the actual values of the data, and then we want to calculate the distance from the mean. So 30 was the one furthest away, right? How far is it from the mean of 70? It's 40 away. 60 is 10. 70 is 0 away. It is the same as the mean. 90 is 20 away. And 100 is 30 away. Right, so those are the distances from the mean. Standard deviation, it's a single number of a data set. It is the average distance from the mean. So take all of these and average them. So there are there are 11 students, so there's 11 scores. So this overall mean, the mean of all these distances, I'm going to add all of those up and divide by how many data points there were, which would be 11. I'm actually physically adding them up here in my calculator. Right, so I think I get 160 out of 11. 14.5. So the average distance to the mean is 14.5, or about 15. So the average score from the mean is essentially 15 away from 70. Okay. So let's compare that so we can start getting an idea what the purpose of standard deviation is and get some intuition. This is all about building our intuition for right now. Right, so this scenario here, do you think the average distance, which is our new idea for standard deviation, is going to be larger, smaller, or the same? Okay, so the data set looks very similar. So if you want to go back and forth between them a little bit, so there's still a 30, there's still 100, there's way more 70s. And so what exactly happened? Some of I think the 90s and the 50s scored a 70. So slightly different scenario, maybe like a slightly different class or a different quiz, and there's more people getting 70 this time, and less people getting some of the other scores like A's and the F's and the D's, I think. Okay, so this scenario here also has a mean of 70, but now more of the values are at 70. And so our goal is standard deviation to describe the average distance. And this is best done by not actually computing it if we don't have to. Right? It even just says, do you think? So if you imagine listing it out, but we're not actually going to compute it, the mean is still 70, 30, 60, 70, 70. So I'm not going to compute everything, but I can kind of imagine it. So the data points are, that's what this list is. The distance, so the 30 is still 40 away, 60 is 10 away, and all those 70s are 0 away. Right, so what's the big difference in our list of distances? Because that's the one we actually average. These distances have much more zeros in the list, and those used to be numbers larger than 0. And so when I average that, that new average distance is going to be much lower. So this mean is going to be much lower. And we don't have to calculate it. There's a lot more zeros in that list. You know, if you have similar scores to someone else, but in one, similar scores in a few places, and then in some places you have worse scores, or they have worse scores, it's going to be lower. Okay, so this is going to have much smaller average distances. And you can actually average that out. I forget what the average is. I think the new one is around 7 or 8. You can go ahead and try calculating it if you'd like. Right. So here are some questions, meant to be done in a group. You can pause here and try a few of them, and then check your work. I'll go through at least a few of them and see how we do. Okay, so to check so notice it says about developing intuition, And so first you'd want to try not calculating, and then if you need to, calculate the average distance. I'm probably not going to calculate the average distance to save us some time here. So these two scenarios here, which class has the smaller average distance? So just imagine writing out the distances. You don't have to write the full list, and then you would average them. We can write out a little bit of the distances. So for the first class, again, the triangle in color and printed, it's blue. If you pick up the one from the bookstore, it's printed in black and white, but you can open up the PDF to see the difference there. So the triangle represents the fact that that's where the mean is. So the mean is at 80. So those two 70s have a distance of 10. There's a bunch, I'm not going to count how many are at 80. Those are zeros. Okay, let's try to imagine the rest of the distances and then compare them to, that's actually class B, the one above. Let's compare that to class A. Right, so the 60, the 70 is this time the mean. So those two 60s each have a distance of 10, and then a few zeros. And then the two 90s, the two 80s have 10, just like the two 90s in class B. So these two classes have the exact same pattern in their scores relative to the mean. And so these two distances are going to be equal. If I add up all of these and divide, and there's also the same amount this time of scores, I think there's the same amount, so I'd be averaging exactly the same way. So these two classes would have the same average distance. What we're going to later formalize that to be the same standard deviation. And so why? They have the same distances from the mean. And you can maybe explain this just a little more simply. These two data sets are actually almost identical. All the numbers are actually a lot different, but in a sense they're very similar. The data is just shifted. And so when you kind of pick up, copy and paste and move data, which sometimes you need to do, you just need to realize, oh, add back 10 to everything. Everybody gets 5,000 for something. So in that sense, the spread of the data isn't changing. Our goal right now is to talk a lot about spread. Standard deviation is a measure of spread, which is what we're trying to get to. Okay, repeating again. So same question, which has the smaller average distance, or if not, which one is equal? So imagine calculating the distances. And your goal at the end of this is to answer which one is more spread out. I'll give you a small clue here. This one, they're not equal. So in case you thought that right away, when you thought they were equal, you might have said, well, there's some at 40, the minimum is 40 and the maximum is 100 for both of them. That's why we made this question in particular. So this one is not equal. One of them has a different average distance from the mean, and one of them has a smaller, specifically. Okay, so let's take a look at class D. That's just the one listed first. And so the mean on both of these is 70, right? And so you can see the shape is different. The centers are the same. And so what I'm letting you know is the spreads will also be different. And so we're trying to build that intuition in case that's not clear yet. So the 40 for the first one has a distance of 30. And then there are two 50s, so distances of 20. 60 has distances of 10. And there's a lot of 70s. So a lot of distances of zeros. And then repeats symmetric on the other side. So then you would imagine averaging that. All right, for class C, the two 40s have a distance the same of 30. The two 50s has a distance of 20. The two 60s a distance of 10. Okay, so how to compare this one? If I imagine averaging the two sets of data here, the big difference is how many values are right at the mean. This is the big difference this time. There are some small differences. This is the big one, though. So in Class D, there are much more values at the mean, which means much more zeros in the list, which means that's going to have a much lower average. So which one is smaller? Class D. Smaller average distance. Take all the distances and average them. Class D is going to have a much smaller average. So this time we had a kind of a different reason what ended up happening. Again, you don't have to calculate these, especially if it makes sense. And then feel free to go and verify and calculate it. They don't have the direct answers written down, but go and on your own you can calculate, and you'll find that Class D is smaller, in case you don't believe that yet. So this answer for Y is a little different. I would end up saying there are much more values near the mean proportionally, compared to the other one. So even if you kind of group the 60s, 70s, and 80s as being close to the mean, for Class D, that covers a high percentage of the data, and for Class C, it doesn't cover as much of a high percentage of the data. So there are more values proportionally, because I don't think each of these actually have the same amount of data, but more values near the mean. Okay, so that is a different scenario. They actually have the same overall range, but how they're distributed, especially near the mean, can produce much different in the future standard deviation. Right now, we'll just call that average distances from the mean. Right, and then moving on. So it's a much more odd scenario now. We have Class F with a few 50s, a less amount of 70s, and a few 90s, and a Class E with a 40, 100, and some 70s. So which class has the smaller average distance from the mean? The same idea again. Okay, again, these ones are not going to be equal. And so we'll cross that off, even if it's not clear why. We're going to cross that off. So let me tell you a common error here to start. And again, you can always pause to try problems. I'm going to kind of just try and go through them. So Class E, the overall range, I believe we've already introduced that term. The overall range, right, goes from 40 to 100. So the range is 60. You subtract the max minus the min. And the range for Class F is 50 to 90, so the 90 minus 50 is 40. So the range for Class E is larger. Range is a way to describe spread, but it's pretty bad. In certain data sets, it can be reasonable. Most of the time, it's not reasonable and not a very good way to do it. So what we want to use are our better versions, something like IQR, or the quartile, just quartile 1 through 3 instead of the range, and this new topic, standard deviation. Okay, so let's imagine the distances again. So for F, what are those distances? So the 50s are 20 away. There's a few 20s. There are 2 zeros with the 2 70s that are at the mean, and then the 90s are also 20 away. And 3 or 4, how many? 4 20s, so I didn't write all of those down. What about for Class E? So this one was a bit of a trick question. The 40 is 30 away. And then lots and lots of zeros. I'm not going to count that. And then the 100 is 30 away. So which of these two, when you average this new list of numbers, is going to have a smaller average? So think about it a different way. Would you rather have a score, would you rather have a scenario, we're going to think about the larger one now, where you most of the time scored 20, and only twice scored 0. Looks like out of maybe about 10 times for class F. I think there's about 10 values there. Or would you rather have scored 30 twice, just look at those distances, two 30s, and scored 0 a bunch of times? If you take those two averages, E is going to be quite a bit lower. So the average for F might be like around, you can add them up. It's going to be less than 20, but maybe 17 or 18. And the average for E is going to be quite small at around 4, 5, something like that. I have these written down in my notes, but I don't have those out. So class E is going to be much smaller average distance. That data set includes lots of zeros. The fact that those 30s are just a little bit larger than the 20s is not going to balance out that most of the data is 0. So Y is really the same as the last point, more values near the mean. If you kind of circle how many values are near the mean, in class F you're not circling most of the values, which means most of the data is kind of far from the mean. In class E, and it doesn't have to be exactly, we're using very simple cases right now, but if you circle values near the mean, you're circling almost everything. And so much more values near the mean. Right, and just I want to point out that the standard deviation kind of involves two averages. You have to know the overall mean of all the data, the normal center. Then you calculate all the distances to the mean, and then you average that once more. So there's two average processes along the way. So we're going to use the word average a lot. All right, draw a dot plot of 5 scores that has a mean of 70 and an average distance from the mean of 0. This one you definitely want to pause if you're going to try this question. So if you did and you tried this, there is only one way to do this. A standard deviation of 0 is only going to come about when each of the data values are the same. And so if your standard deviation, or sorry, average distance, we'll get to standard deviation in the next activity. If your average distance is 0, the only way that worked out is if each value is the same as the mean. So each value is the same as the mean. And this is from something very subtle that I did not mention on purpose earlier on. When we were calculating how far away things are from the mean, we weren't purely subtracting. Because in a math formula, you would need to decide which way you subtract. And this time we didn't have a way we subtracted because, I can show you. In these distances here, ones that were below the mean were positive, and ones that were above the mean were still positive. And in any normal math formula, if you were to do that, you kind of have to switch the order of subtraction. So something is happening there. But naturally, most people are very familiar with if you say distance, you know to make that positive. And even sometimes we like to make things positive maybe when we're supposed to. So there's something kind of subtle happening here. For some reason, our number is always positive. So the distance from the mean can't be less than 0, but we were already working with that, and you might not have thought much about that already. That's fine, that was on purpose. So this must be something we need to think a little bit about. Right, so here are 3 data sets, and we're going to calculate and compare. I'm going to rank them for which have more, which has the most variability around the mean. So this is our professional term for asking which has the largest average distance. So variability is spread, and so a larger spread would mean a larger average distance. So that's the vocabulary. That is very professional. If you just said had a larger spread, I think that's better day to day in a discussion post or something like that in class. So we want to look at these and decide which has the most and the least variability, which means we're ranking them. And so the shortcut way to do that which you can imagine keeping notes down here, when comparing to how do you identify the graph with the smaller deviation or distance or variability. A lot of those words are kind of interchangeable for us. I ended up kind of circling the middle and then asking how much have you circled. So if you circle the middle of the data set, proportionally, have you circled a lot of it or not as much, especially when you're making a comparison? So in these, kind of circle the middle. You know, where the middle is there's not a lot of numbers here. And we don't even know what these values are. But so we're just going to have to be consistent. So I've decided to circle everything except the outer data values, and just to get an idea. So which data set has the most variability is going to be the one that has the least amount of data near the middle. And so it's going to be B. B, the middle green ones there, I've only circled one of the data values. This looks a little bit like one earlier. And the least is C. That one I've circled almost all of the data. And again, this is best if I'm comparing them. But even within a data set, you can use that to answer just a general idea. Is this going to have a large or small standard deviation? Are you circling a lot of the data? All right, I believe that is the last question. So it's the introduction to the concept of standard deviation. I believe we now introduce the standard deviation. So it might be a good time for a break. Module 7 is a little bit lengthy. I'm going to continue on here. All right, so what we were calculating earlier, and then you'll see it in the beginning of the notes also, is actually not called the standard deviation. The average distance from the mean is called the average deviation from the mean. Deviation is a little bit more common stats word than distance. I've already been saying it in the standard deviation. But the average one here, this is what we were doing earlier. And this is what we're going to switch to, called the standard deviation. So I'm going to point out really quickly how it works. It's very similar. It doesn't look like it. I'll point out also what our other formula was. So one thing I pointed out was that in a math formula, the way you subtract probably can't just switch around another one. So how do we ensure that it always stayed positive? And so we do that with absolute values. And so we guarantee that the subtraction that calculates the distance, and I realize I need to introduce one more formula, a few explanations of the symbols there. Okay, so in all of these ones, X represents each data value. These are weird formulas that repeat for each value. The X is going to be the one that represents all the different values done one at a time. X bar is a common symbol. You have already seen this in the notes in Module 5, learning about the mean. And so this is the symbol for the mean. Right, that's the normal average. Add everything up and divide. We give it the symbol X bar. N in stats context always means the amount of values. So N and sometimes M always mean counting something in most math and sciences. And so in specifically stats, N is always how many of the things. Okay, so the formula for the ADM, which was technically what we were doing earlier, says, and I kind of skipped to the positive. So there are 4 steps here. So the first step is that subtraction. And then the second step is really that absolute value, especially when that subtraction was negative. We go back and make it positive. That one we did in our head naturally earlier, so those 2 steps were combined before. Then This step is kind of done separately. That E symbol, which you have also already seen in the notes, I might have written it down in the videos here too. So that is called sigma in math. It's a Greek symbol from the Greek alphabet, and it's sigma. Um, and sigma in any math or science context is very consistent, always means to add everything up. And so it's adding up whatever is right next to it, and so that means add up all those distances. These pieces here are all of the distances. So add up all the distances and then divide by n. And so you're just dividing by n once. That is the process we did earlier. First step, subtraction. Second step, make it positive, in case it wasn't, especially. Third step, add them all up. Fourth step, divide by how many. And combined, those are the idea of averaging. Okay, ADM is gaining popularity. It was never popular before and is still never going to be as popular as standard deviation. But with more use of calculators and computers in statistics, kind of only using calculators and computers now, it's a little more common. The standard deviation was much more popular historically because of a handful of different reasons. One is calculus, so it's a little hard to describe why that's important. But statistics actually has calculus in the development of some of the kind of really advanced formulas. And some other things about how absolute value works can be very difficult. So there are some things that meant this was the formula more popular early on when this was developed. A lot of statistics isn't that old, which is a little weird to think about. A lot of math is really old, hundreds of years at least, like calculus. Stuff like trigonometry, geometry, and algebra, thousands probably, up to thousands of years old. Statistics, about 100. Some of the earliest statistics was in the early 1900s, maybe late 1800s. Some of the earliest ideas, have been a little common, but so things are still changing. Some stats are still being developed, and what's popular or not still changes. Okay, so we had those 4 steps: calculate the distance from the mean, make it positive, and then average it. Essentially, are steps 3 and 4. Those same things happen here. So we still have that subtraction. That's step 1. And instead of absolute valuing, if that's a word, we instead square it to make it positive. Right? Anytime you square a number, it's positive. Then we add it up. That's still step 3. So these formulas are very difficult to read, and there's actually even more details that need to be here to really correctly describe how you do this. And so this is more of a shortcut version of the formula, because we will not be doing formulas by hand. And they're actually not something like the quadratic formula where you plug in the numbers and calculate. They actually are a process, and so that's why I'm labeling it here. But day to day, you will not be replicating like this. This is just, we do have to go through once and explain the formula. All right, so we do add them up because we are going to average. We add them up and divide by how many. So that process is still an average. Step 4 is divide. Then this has a separate final step of taking the square root. Notice though, it's dividing by the amount of numbers minus 1, n minus 1. Why? That's like a stat fun time, aka office hours. That's like a stat fun time topic. That's a little difficult to explain. And the last one though, this technically has one last step. That 5th step is square rooting the values. Square rooting just the single number. I'll show you, we'll give you one example. And that's because you squared it earlier. The purpose of your squaring was to make it positive, and so now we need to square root it to bring it back. Okay, so we are going to go through an example. Right away we're trying to remind you, you're not going to do this. You do it once if you'd like. Don't do it more than once. We will use technology to find the standard deviation, skipping down one paragraph. Okay, but let's see what it looks like, though. Sometimes working through a formula can help us understand it, maybe. Okay, so the mean is 10 of these numbers, and so we need to go through those steps. So step 1, I'm going to just write all the numbers down. So step 1, I don't need to. Okay. 5, 6, 10, 11, 18. So those are all the values x. X in a stats formula means all of the individual values. And there's actually some more particular ways to label them. If you really had to understand what the day-to-day use the formulas, there's better ways to label them. Okay, so our first step is supposed to be x minus x bar. So x minus x bar, so you take the values and subtract the mean. And so the mean is 10, you can verify, but if you add them up and divide by 5, because there's 5 numbers, the mean is 10. Right, so 5 minus 10 is minus 5. 6 minus 10 is minus 4. 10 minus 10 is 0. 11 minus 10 is 1. 18 minus 10 is 8. Right, next step in standard deviation, not ADM. Right, so in ADM would be just make those positive, add those up and average them. In standard deviation, the step is going to be to square them instead. And so each of them needed to be squared. We could have done it earlier, but we highlighted that as a separate step. So 25 is negative 5 squared, negative 4 squared is 16, 0 squared is 0, 1 squared is 1, 8 squared is 64. Again, the main purpose here was actually to just make this positive. These are the two mathematical ways we have to make things positive. Turns out squaring is actually more useful here, or more practical, even though you might think that that sounds kind of crazy. That one maybe also a stat fun time type thing where we could talk about why. It's a little complicated. That's kind of the difference in what a statistics major learns. A statistics major will go into how you really use calculus and statistics and kind of understand these topics much more in depth. Okay, so our next step is not something we do for each of the values. So we only do it once we add everything up. Step 3 is to add everything up. So to sum, what I'm summing is x minus x bar squared, summing all of those. So, I won't be lazy, I'll write it down. Okay, so take each of those numbers and add them up. Realistically, we will always work with software. You can work with Excel, Google Sheets, or StatCrunch. For simple stuff, though, feel free to have a small calculator out and do things by hand. Okay, so our sum of our deviations from the mean or something like that are the official terms. It's 106. Then we're going to divide that. So step 4 divided by n minus 1. So 106 divided by 5 data points minus 1. So 106 divided by 4 is 26.5. Then that's the number sitting in the square root still. So now the final answer, the standard deviation, is the square root of that. And so that's 5.1. And so this was the same thing that the average deviation from the mean was trying to calculate. And that's what we called before the average distance. It's actually an official thing called the ADM, but it's just not that popular right now. It's gaining popularity, but not popular in general. Standard deviation, by far, much more popular. And so we still want you to think about it the same way, though. the standard deviation is an average distance from the mean. So with these numbers here, the average distance from the mean is about 5. The mean was 5, and so most of these numbers, on average are about 5 away. Right? The smallest number is 5 away, but 6 is 4 away, which is kind of close. The 10 and the 11 are much closer, but the 18 is over 5 away, so roughly that averages to 5. You could verify and calculate the ADM here, and you can see it's somewhat similar. The ADM and standard deviation are not always the same. They're not going to be exactly the same here, though. Okay, so we will always do this with a calculator, with some official calculator or software. You will just type in all the numbers and ask it to find you the standard deviation. So that'll always be quick. But this is what's going on in the background. Okay, what's actually more important than getting the answer for the standard deviation or knowing how the formula works? If you know it describes spread and it works on averages, you're pretty good to go, is using it and knowing when to expect one versus the other. So if we had those cities from San Francisco, city A and city B, San Francisco and New York, the city temperatures, and you were trying to think about which one should have a larger standard deviation, your goal is which one is more spread out. Spread out specifically from the mean, not necessarily the overall spread. Which ones are more spread from the mean center? Okay, and so, which one is going to have a larger standard deviation? Apparently, the answers are 4.4 and 16.6. And so, standard deviation for San Francisco, which was the first city, is going to be the 4.4, much smaller, much more compact around the mean. Standard deviation for New York is 16.6, apparently. You could verify if you wanted to there. Right, unfortunately this question spreads on 2 pages here. Which do you think will have a larger standard deviation? So we're collecting 30 random students. I don't know if I've said this yet. LMC is a school where we made these notes. So pretend it said Crafton anytime you see that. So a random sample of 30 Crafton students and how much you spent per unit. And then a random sample of 30 college students in the US and how much they spent per unit. Which of these has a larger standard deviation? And this is a roughly real-life question, and it's already a little complicated. So technically, you all spend the same amount per student as Crafton students and as California community college students. I think all California community colleges charge the same thing, I believe. I think it's $46 a unit, right? And so everybody at Crafton spent $46 a unit, so the standard deviation is 0. But you might say, okay, there's financial aid, could bring that down to 0. You can possibly get paid a little bit, right, to take a class, depending on how much financial aid you get. So 0 to 46 with a lot of 46s and some bringing that down and something like that. Okay, so it's a little complicated. Let's think about that compared to random sample of college students in the US. Well, if I take a random sample, I'm going to get some community colleges across the country, some public universities, right, like our Cal States and UCs, which have subsidized tuition, so they are a little cheaper, just like our community colleges are cheaper. And I'm going to have some private schools, so they're going to be much more expensive. Even when I factor in financial aid, to give you an idea, if a school costs very commonly $30,000 to $50,000 a year, that's somewhere between $1,000 to $2,000 an individual unit. So that could easily be, for this class, could cost them $5,000 to $8,000 sometimes. I don't really recommend those really pricey private schools personally. So even if you kind of say, okay, most people are going to be from 0 to 46, if you don't include financial aid, this question's even easier. And if you look at across the country, how it's going to change, it just allows private schools in the mix, and even public universities, right? Cal States are, what, 7,000 to 10,000 a year? I forget what that means per unit. That probably means maybe like 200 to 300 a unit. something like that. And the UCs are a little more expensive, and then private schools are very expensive. Um, so in general here, and we're trying to highlight, you've made the financial smart choice in coming here, that very clearly, which has, larger standard deviation. A random sample of 30 college students is going to be much larger. It's just going to include a lot of values that cost hundreds of dollars per unit, even if there are some values the same, including financially. Right, so that answer again, across the country. So, also just to discuss, prices in case you're curious. Okay, so this scenario here, which distribution has the smaller standard deviation? Right, so standard deviation, average distance from the mean. We can use the same trick that we did, no, not trick, but method that we did mentioned at the end of 7.1's activity. Circle the middle of the data. Have you circled a lot of the data, or which one proportionally have you circled more? Those are going to produce smaller distances, even if they don't have the same amount of data, that's okay. So a lot of students here, some students here choose A because it's flat and it feels symmetric. That is not at all the purpose of standard deviation. Standard deviation is trying to tell you how many data points are near the middle if it's small, and if it's large, it will mean roughly there's not a lot of data towards the middle in a sense. So the smaller one is B. When I circle the middle and try and look at the middle, I'm getting a lot of the data values there, so I'm going to have a lot of small distances. Compared that to A, when I circle the middle, I'm not circling near as much of the data as a proportional percentage. Right, so same answers as before, more of the data is near the middle. Right, and one last question here. If standard deviation of quiz scores on a checkpoint is 0, what do we know? Does that mean everyone scored 100? Everyone failed? Everyone got the same score? It's impossible to tell. It's impossible to tell is not a great answer. We probably can figure out something about it when we know it's 0. So be careful with impossible answers or generic answers like that. Actually, all the other ones are decent answers. So we saw earlier a standard deviation of 0, or even think near 0, means that every score was the same, or almost the same. And so if everyone scored 100, the standard deviation would be 0. And if everyone failed, the standard deviation might not be 0 unless they all failed with the same score. That's kind of the right idea. But more specifically, they don't have to all score 100 and they don't have to all fail by maybe getting all 50s. They have to, this general scenario is just a little bit better answer with saying everyone scored exactly the same, which could be 100 or it could be all failing. So pretty reasonable answers, but C is the best one there. Standard deviations of 0 occur when all your data is exactly the same. A standard deviation near 0 means your data is very similar. All right, what does standard deviation measure? Very simply, we want to say spread. Specifically, spread from the mean. So that's the basic idea. Spread is fine as long as you're not resorting to just the range and you're thinking a little bit about the shape. I think it's worth kind of flashcarding its official definition as an average distance from the mean. Let me clarify, official. So that's a partially official definition. It's really the purpose of standard deviation, the average distance from the mean. It's not a true average because of the weird squaring and some other oddities about it though. So those are two good examples, spread in general, spread from the mean more specifically, and as an actual explanation, the average distance from the mean, which is technically ADM, but is really the purpose of standard deviation. Right, and I don't think I'm going to compute examples. I'm going to finish this off here, but Mean and standard deviation are used together. So we have median and IQR. Those are both built off the quartile style of measurement. Mean standard deviation is built off the mean, right? If you want to very carefully read the title of the module now, quantifying variability relative to the mean. So calculating spread using the mean is a word-for-word interpretation there. Calculating spread using the mean. Okay, and so I'm going to make this pretty quick here. Just like we used IQR and quartiles, Q1, Q3, and the idea of IQR, we can do the same thing with the mean minus the standard deviation and the mean plus the standard deviation. This is actually quite popular later at the end of the course. We do this in a few different scenarios, but I'm just going to leave this as like a pretty quick idea here. So here are shoulder girths, so like distance around in some way for shoulders for male and female. So the averages is 116 versus 100, but that doesn't tell us exactly all we need. You know, we do have a picture there to finish it off, but how much they overlap and how much they're spread out tells us a much overall better answer. And so if I take the standard deviation for men was 6.5, so here are the two means. I'll put a box around the men and a circle around the women's data. The standard deviation was actually about the same for both. And so if we take that and add and subtract from the mean, we get a really good, roughly middle half of the data. Quartiles and IQR, Q1 to Q3, is exactly the middle 50%. This is something similar, and we'll talk more about that in a future module. So mean minus and mean plus standard deviation, 116 for men, 6.5 standard deviation, add and subtract. So a typical men's shoulder girth is between 110 and 123. And we could repeat that for women, take 103 and add and subtract. So one way to represent is just plus and minus, means to do both. 6.5, it's a very common stats symbol. The smaller size is 93.8 up to 106.8. And so here is an easy way to see how different men's and women's shoulder sizes are. The typical interval is a good way to phrase this. Doesn't overlap for men and women. And so this gives you a very strong, concrete, kind of agreed upon way how to describe that men and women have different shoulder sizes. Their means were different, but their standard deviations were also kind of small in context. And so this middle group, try that again. Middle group of female shoulder sizes compared to males is quite a bit different. Okay, so there are some more examples there. I'm going to skip all of those. I believe this is the end of our Unit 2 and Module 7. I will have a separate video describing this next piece here, or maybe just a post about it. And so you might be wondering, what are those data project things I need to do? And so these are at the end of most of our units. I think one or two don't have them. And in class, this would be, you'd make a poster. I'm going to have you make just a typed up answer to this, like a report to this. And so in your report, you'll give us a statement of the question. We are giving you all the questions. The data is going to be on StatCrunch, so I will go through and show you how to find this. But, you know, one question you could research, there's a movie data set on StatCrunch. I'll show you how to add that. So we'll get to this soon. Action and adventure versus other types of movies, and you compare at least one quantitative variable, and use all of these things in your report, 1 to 2 pages, calculating some values and graphs on your own from StatCrunch to answer that question. We are giving you that research question. And so these are the ones you have to do a few times over the course of the semester. I believe, like for A grade, I think you need 3 of these. And so you don't have to do them for most units, you need to do them for a few. They don't have a specific due date. You should get them done soon after finishing that unit. So after you finish a unit on Canvas, you have this and the mastery quizzes to worry about. Those are the 2 things. More of the mastery quizzes than these data projects, though. All right, I'm going to stop that here. This finishes Unit 2, and we'll recap again for Unit 3, Modules 8 and 9.